Welcome to part 1 on real zeros of polynomials. To graph a polynomial by hand, we need to find its zeros. So far, all the polynomials we've graphed were factorable. What if factoring a polynomial with one of the methods we've learned in another math class is not possible? Let's pause here before I start going into great detail about all the theorems to remind you that although all these theorems work, and they're pretty cool, you have this thing called a calculator. And I cannot stress this enough. Use the dang calculator. If you can't use your calculator, these theorems are going to be even more important to you. But if you know your instructor is going to give you a calculator for your next exam, these theorems are only to help you throw out extra roots or extra zeros of a polynomial that otherwise you would have to test. But they're pretty cool, and they will help you guide your choices along with your calculator to determine what roots or zeros of your polynomial you have. The first theorem is the rational zero theorem, and it says if the polynomial p of x with degree n and has terms all the way down to a sub 1x plus a sub 0 has integer coefficients, and remember integers are like plus or minus 1, plus or minus 2, plus or minus 3, etc., then every rational zero of p is of the form p over q, where p is a factor of the constant coefficient a sub 0, and q is a factor of the leading coefficient a sub n. So in the first example, we have find all the possible rational zeros of p of x equals 32x to the fourth minus 76x to the second minus 191x squared minus 71x plus 12. If we want to know what p over q is, I'm just going to write that off to the side, p over q, and I'm going to list all the factors of p. Now remember, p is a sub 0. That's my constant term. So I have p equals 12 in this case. I also need to find q. Q is the leading coefficient a sub n. So in my particular case, q is 32. Now we need to list the factors of p over q. This is a long, crazy process, but you will need to know how to do this. So 12. We have 1, 2, 3, 4, not 5, 6, not 7, not 8, not 9, not 10, not 11, and 12. Same idea in the denominator. 1, 2, not 3, 4, 8, 16, and 32. Now, this is where it gets pretty intense, if it wasn't already to you. We have to list all the possible combinations. And if that's not enough, remember you could have plus or minus. So we have to list all the possible rational zeros, and I'm just going to do this in a very methodic way. I'm going to start with the first numerator value, and I'm going to list it off. Plus or minus 1 over, and now I'm looking at each denominator. 1 plus or minus 1 over 2 plus or minus 1 over 4 plus or minus 1 over 8 plus or minus 1 over 16, and plus or minus 1 over 32. There will be some repetition because some of these are going to reduce to the same thing as other rows. But we need to list all of them, and then we'll clear the ones that are multiples. And now I'm going to move on to the numerator of 2. Plus or minus 2 over 1, plus or minus 2 over 2, plus or minus 2 over 4, plus or minus 2 over 8, plus or minus 2 over 16, and plus or minus 2 over 32. Okay, 2 is done. Now I'm going to move on to 3. 3 is plus or minus 3 over 1, plus or minus 3 over 2, plus or minus 3 over 4, plus or minus 3 over 8, plus or minus 3 over 16, plus or minus 3 over 32. I got rid of the 3 now. Now let's work on number 4. Plus or minus 4 over 1, plus or minus 4 over 2, plus or minus 4 over 4, plus or minus 4 over 8, plus or minus 4 over 16, plus or minus 4 over 32. So 4 is done. Now let's do 6. Plus or minus 6 over 1, plus or minus 6 over 2, plus or minus 6 over 4, plus or minus 6 over 8, plus or minus 6 over 16, plus or minus 6 over 32. Then we'll work on the last one, 12. Plus or minus 12 over 1, plus or minus 12 over 2, plus or minus 12 over 4, plus or minus 12 over 8, plus or minus 12 over 16, and plus or minus 12 over 32. That is a lot of possibilities. Let's go ahead and cross out any doppelgangers. So this first one is equal to 1. So we have this 2 over 2 is equivalent to 1. Anything else here? The 4 over 4. And I think that's everything. Okay, so now let's look at the 1/2. Plus or minus 1/2. We can cross out the plus or minus 2 over 4, plus or minus 4 over 8. Okay, now let's look at plus or minus 1 over 4. So 1/4. So we can cross out the 2/8. We can cross out the 4/16. Now let's look at the 1/8. 1/8 is equivalent to 2/16 can go away because that would be 1/8. And 4/32 could go away. I think I got all of them. This is easy to miss a few. Let's look at 1/16 now. We could get rid of the 2/32. All right, I think I'm good for that one. Now let's move on to the next row. We have a 2 over 1. So let's cross out anything that is equivalent to 2 over 1, which is just 2. So 4 over 2 could go. Okay, I think that's everything for the 2. Now let's try 3 over 1. Anything equivalent to 3. 6 over 2. 12 over 4. I think that's everything there. Let's try 4 over 1. I'm not seeing anything. Now let's move on to 6 over 1. Well, there's a 12 over 2, so we can cross that one out. Let's go ahead and try 3 halves. I know that 3 halves is equivalent to 6 fourths and 12 eighths. Now let's look at 3 fourths. 3 fourths is equivalent to 6 eighths, 12 sixteenths. Now let's look at 3 eighths. That's equivalent to 6 sixteenths and 12 32nds. Now let's look at 3 sixteenths. That's equivalent to 6 32nds. And so we have now identified every single one of our possible roots. Notice that all the ones crossed out were duplicates. And so we have this interesting pattern emerging. I don't know that there's any specific pattern in particular. This might not always look the same way, where you have a row almost x'd out, a row, and then the rest x'd out. Sometimes it follows that pattern. Now let's apply this in a real life situation. Let's say you have this giant polynomial. It's of degree 4, which means at most you can have 4 roots, or 4 zeros of the polynomial. And let's say they look like they're about at these locations. Let's say this just barely crosses in the positive region. So you can, maybe think, okay, well, maybe that is a positive 1/8, and you can put a little question mark there. If that's a 1/8, maybe this is 1. And the next one we'll look at, maybe that's a 3. So now we need to be curious about this last one here. I don't know for sure, but it looks like it's somewhere around -1.5. So if you look at all of your roots, and maybe you can't quite figure out the decimal yet, but you can figure out approximately where your roots are based on your graph. Then from there, you can start using synthetic division to divide out the common factors. If there's one thing you take from this video, I hope it is to use the theorem I just showed you to throw out values you don't need. So here are the steps to find the rational zeros of a polynomial. 1. List the possible zeros using the rational zero theorem. 2. Divide using synthetic division. If the remainder is 0, you found a rational zero. If you don't have a remainder of 0, you should throw out the possible 0 and try another one. I would keep trying ones similar or close, because hopefully with your graphing calculator at your side, you will be able to identify which ones are going to be very possible and which ones are clearly not going to work. Repeat this process until you have a quotient of degree 2 or smaller. This is very important because at this point you can use the quadratic formula, which is step 4. Don't keep using synthetic division when you can use the quadratic formula to get your last 2 zeros. And the reason I say use a quadratic formula is because a lot of times the zeros that are left are not real. They're imaginaries. And so if they're imaginaries, it's not going to be obvious to use synthetic division. You have to use a quadratic formula or it'll just be a big mess.